universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, and welcome. This is Mark D'Antonio, and I think I'm Mark D'Antonio. That's Daryl Mason over there, and that's Tara down there. And we are Sky Tour Radio. It's great to be with you again live. This is a live show. We've been away for a while. I had conferences I had to speak at and so forth. I had to get COVID in the meantime, just to be like everybody else. Okay. So I'm fine now. Everything is fine. And I just wanted to welcome you guys. Hi there, Daryl. How's it going?
Hello, Mark. I'm nominal, thank you. Warp engines are online.
Okay. All right. That's like, warp core is solid. Everything's in the green, Okay.
Yeah.
And how about you, Tara?
I'm doing good. I've missed you guys.
No,
Glad to be here.
I'm sure you've been aiming too. But,
I have.
No.
Aiming to see the show. So
that's right. That's right. There you go. So this is Sky Tour Radio, and we're our other co-host Amanda Curran is not with us tonight, but she'll be back next time. And this radio show is sort of an outgrowth of our remote observatory that we run called Sky Tour Livestream. Sky Tour Livestream is visible from our portal. You can go to skytourlive.com or skytourlive.org and check us out. And you can find all these gorgeous photos that we shoot from our remote observatory out in the Arizona desert. We streamed last night until 1 a.m. Daryl, you were with us. We had a great time, didn't we?
We did. It was a cool stream.
Yeah, it was.
It was actually over too soon. I was still raring to go. You pulled the rug out from under me.
Well, I actually I had to err on the side of weather. I mean, there were some rain clouds coming in from a long distance.
Yeah.
And so I had to err on the side of caution with those.
Well, at least, we got in some before the weather for a change.
Yeah.
Speaking of, we're looking at about 80-90% chance of heavy rain here, flash flood warnings and all that stuff.
Wow. Yeah. Yeah. Here I'm looking at a thunderstorm out back here. Yeah. And, if you see this happen, you'll know that we have a tornado or something going on. But, honestly, the weather is pretty good out in Arizona in general. Right now, it's the monsoon season out there. And all it means for monsoon season is that it might rain a little bit.
Well,
right?
There's humidity too.
Oh, yeah. Tell us about the humidity, Tara. You got to hear this, guys.
It gets up to like 30% or something,
Heaven forbid. We live in normal days at 60% humidity around here.
I don't know how you do it.
30% humidity. I'm going to tell a story.
It's more than that, actually.
On a good day, we get single-digit humidity here.
Wow.
Nice.
See, that's what I like. I was in Phoenix for, I think, working on the observatory. I stepped out of the shower and I started to dry myself off with the only towel I could find. It was like a dish towel. And it was more than sufficient because as I was drying off, just moving the air around with the towel was drying me off. And I was totally dry in just a few minutes with a dish towel. Right now, I checked the humidity. It was 6%. That's not a lot of humidity in the air, so that's very low moisture. But you know what? I like that very much because that's good for equipment and it's excellent for, when you want to do something remotely.
Makes your hair frizzy too.
Yes, it does.
I don't know about that.
I do.
I mean, I don't have that problem. I guess but I do get Einstein here. So if it goes way up there,
go through Carmex or chapstick like crazy here, and
Yeah.
the ladies like to lotion up, and it really sucks the moisture right out of you.
Yeah, it does. It does. That's for sure.
But we're getting the monsoon here too.
Mm-hmm.
Clouds up every day, may or may not rain.
It's actually alleviating in Arizona a little bit from what I'm seeing now. Now Tara lives there. I'm not living there, not yet. I'm planning on it, but I'm not there now. But I believe from talking to other people out there that the monsoon is starting to change. The directions of the fronts are now changing.
Yeah.
And that's a good indicator that it's over, or starting to be over. And that afforded us a couple nights of clarity that we could actually take advantage of this past week.
Yep.
You know?
Yeah.
So, and when we talk about this remote observatory, well, what is it? I mean, we take these pictures, right? And if you go to our portal site, skytourlive.com, you'll see this beautiful entry portal. I should actually just do it. I should show it rather than
Why
talk
not?
about it.
Yeah.
I don't know. I guess. All right. All right. You twisted my arm. I actually
Do it.
I do want to do it. And I'll tell you why, guys. I want to show you what is going on, and how you can access all the beautiful pictures that we create. I think that's
very cool.
Probably a good thing. So, all right, I'll share the screen just for now. Just show you this, okay? Okay, this is right here. This is our SkyTour live stream observatory portal, and you can go to SkyTour live stream. This will take you to the actual. Site where it stems from. This is our website right here. Okay. And we're actually live right now, and in SkyTour live stream, we're sending this to our channel, right? And also, if you scroll down the next section, you see this thing says, "I want cool pictures." It'll take you to an online database where you can drill down through some directories and see the pictures we took literally seconds after we took them, because we're shipping them out of the Arizona desert, going up to the cloud, and making their way to anyone around the world in just a few seconds. So that is really performing very well.
That's awesome.
Yeah, and we have a lot of storage now for that uploaded. We have a terabyte of data that we have available up there. We're filling a fraction of it right now. If you scroll down more, you can actually get prints now, and our photographic prints are really they're astonishing. I'm amazed at how well this service works. And let me kind of show you here a little bit on that. So if I turn on my lights here, okay, and just for a moment, let me bring me up here. How do I do this here? It's got to be a way to. No, that's Daryl. I want me up here. I don't know how to do it. Maybe this way. I'm not sure.
I want me up there.
Yeah, I'm sure you do. Let me see if this will do it. Okay, hold on. Okay, there we go. So this is an example of one of the prints. Okay, this is the Elephant's Trunk Nebula. And this is an example of like a 30-second photo taken with our telescope. Look at the beautiful nebula out there. And this is printed on regular paper.
Wow.
You know, just regular, but it's a high quality photographic paper. And then the other thing you can get with this system, we can print these on metal. You can print them on canvas. So here's a canvas version, and it's actually got a stand to stand up, or hangers. They come with hangers that just hang them on the wall. This one is called a canvas wrap. So the image wraps around the canvas. It's a small one, but this is part of a supernova remnant that we're going to talk about later too, by the way. And we have several dozen of these online that you can just go select and check what you want. You can get framed under glass. It's amazing what they have available. You know, I'm really amazed at how they can do this. So that said, I think that it might basically behoove us to consider the fact that, you know, SkyTour live stream is a fun place to go to check stuff out, you know, and I would hope that people would take advantage of it, you know, like if you scroll down further, you can see our photo gallery. All right. And these consist of pictures we just took. Like this was taken, Daryl, you were with us when we took this photograph just the other night. This is the Crescent Nebula.
Yep.
Yeah, a beautiful nebula. And then he was also with us when we took this photo. This is the Veil supernova remnant. It's the entire thing. It's a composite.
Wow.
That black square is where I didn't have enough photographic data. I took 1, 2, 3, 4 photos, but not a fifth. And so I didn't quite get it, but that's okay because there's only a little bit here. This gives you the idea.
Yeah, Hubble does that too. That's okay.
Yeah, that's right. It's a thing now, This is the Boogeyman Nebula, kind of on its side,
Oh, cool.
Yeah, and this is M101, the pinwheel, a spiral galaxy that's face on to us. This is the Eagle Nebula, Messier 16. The Pillars of Creation are inside there.
Wow.
And this is our full field. Our field is 4 full moons across and 3 full moons tall. Right? This is the Lagoon Nebula complex. This is amazing.
Wow.
In a small telescope, people see some of this nebula. They never see this over here or this out here. And they usually don't see this here or any of this dark nebula down here. We show it. We did this. This is another 25-second photo, and the universe is full of this black dust. I mean, evidence of that is right here. This is a star called Rho Ophiuchi. All right. And this is near Antares. And this is an area full of black dust. And that black dust is my favorite thing in the universe, to be honest with you. Because black dust to me, well, that tells me, this black dust for me is like the quintessential stuff that you really would make the universe from. Okay, it's where you would get planets from. It's where you get other things from. Stars are born in this dark nebula here. This is all important stuff, at least to me. Now, when a star is born out of that stuff, stars also die. And when a star dies, you get a planetary nebula like this, in some cases, for stars about like the sun. And what's left is a tiny little white dwarf in the center. You can see that little tiny white dwarf. Even though this nebula is thousands of light years away, you can see the white dwarf that powers it. Keep in mind that the white dwarf is only the size of the Earth. And this is thousands of light years away, yet you can still see it. That's because this white dwarf is exceedingly bright and hot. It's the core of the star left over after the collapse is done and after it's shed its outer layers. All right. And that's for a star like the sun. But if a star is bigger than the sun, you might get a total explosion. This is a catastrophic explosion first seen by the Chinese in 1054 AD. And this became the Crab Nebula to us. But it's a supernova remnant. All these tendrils are the result of the material expanding into space and hitting other material and twisting and pirouetting around. It's a violent, violent cataclysmic action.
Big bada boom.
Yeah, big bada boom is right. And this is the telescope that does it all out there. This is in our building out there. This is our camera. It's actually in the front of the telescope. And the light comes in through here. So you say, well, why do you have the camera on the front? Well, that'll be for another talk. But look at the skies. I mean, this is beautiful out there. This was sunset out there. This is looking to the right of the telescope in this image. So it's over on this side of the telescope, looking in to the right. And then we have this beautiful scene. And that's also looking out in that direction. And then this is the actual observatory out there. And guess what? Look at that door. I mean, that door says SkyTour Livestream, STLS. And I wonder who did that door.
Who knows?
Oh, I'm sorry. Yes, it was Tara, our wonderful artist, who actually made that door for us. She's phenomenal. And the entire roof of this building rolls right off onto this rail. This is actually a horizontal garage door. And I said, you know what? Why can't an ordinary garage door open and do the job? I just run it remotely from 2,500 miles away. And that was a little bit of a tricky part, but yeah, I figured that out. So anyway, there's lots of stuff we show. The California Nebula. Here's another version of the Veil supernova remnant, all the intricacies in there. And Daryl, often you'll comment on how intricate not only this side is, but the other side that we see.
Yep.
And then this is called the Running Man Nebula. And among the many favorites is the Rosette. This is another star-forming region, an area in space where stars are being formed, and the stars have such hot ultraviolet radiation that they hollow out the middle of the gas cloud in which they formed, and that's why it looks like it has a hole in it. Okay, we're going to talk about this process in just a little while when we look at the James Webb images. Okay, this is the beautiful Heart Nebula. There's the heart, ta-da, right there. Oh,
it looks like a sea turtle.
Well, it does, because it looks like this is the head, this is the flippers. Yeah. This looks like a leatherback sea turtle, as a matter of fact. Yeah.
That up at the top right is called the fish, actually.
That's right, the Fish Head Nebula right here.
Oh.
Yeah,
Could be a seal.
I guess it could, squashed on the road maybe, but yeah.
Roadkill seal.
Oh no. And well, moving on.
Yes.
We also have the Andromeda Galaxy. Look at this beautiful galaxy. And this galaxy, when we took this picture, our sensor is high enough resolution. You can zoom right into some little areas like this and see tremendous detail in there. We can see individual stellar nurseries like that Rosette and the Lagoon Nebula in this, because this has its own version of those stellar nurseries as well. And so too, and this is actually 2 million light years away and heading right for us, by the way, just so you know, in a couple billion years, it's going to hit us, but it's going to sort of go through us and probably convert both galaxies into something new. And we probably have seen what happens with galactic collisions, and we will talk about that shortly when we look at one of the James Webb releases that just came out. But when they're isolated in space like this, this has a companion galaxy pair itself, as do we. We have two and an additional dwarf galaxy that is attached to us in a way. But this galaxy looks like it's held together. But again, it's massive. It has over 1 trillion stars in it compared to our 100 billion, or so. And then right near it in space is this galaxy. This is the Triangulum Galaxy, or Messier 33. This was Messier 31. And you can see little splotches of red in here. These splotches of red are, again, very, very large stellar nursery regions. This one here is massive. That red one right there, that's a massive one. And remember that, because, again, we're going to talk about massive stellar nurseries when we look at the James Webb imagery shortly. And that has relevance to us. Here's one I told you about. This is the elephant's trunk in just the format online. You can get it as a print. You can get it as, you can just download it and put it in your background. There's all kinds of details. And so the bottom line is there's plenty of objects that you can capture. Here is, believe it or not, this is the Orion Nebula, and this is the Running Man Nebula just above it. And whereas I showed it to you, it looked all blue. If you do a really deep exposure, you see all this additional dust that lingers out here, dust from which stars will form and or planets in the future.
It's gorgeous. Wow.
Yeah, we're actually looking at the genesis of future star systems when we look at dark nebula like this. To me, that's my hot button. These dark nebula are the coolest places, and they literally are the coldest places in the universe in general. Then we have stars. Sometimes they pass through dark nebula, and when they do, they can illuminate it. And these are called blue reflection nebulae, but this is the Pleiades, as some of you might have already noticed. And these blue reflection nebulae are caused by the dust grains in a dust cloud scattering the blue light from these hot young stars in this young cluster, right? And this dust is not associated with this cluster. The stars are moving independently of the cluster, and they just of the dust, and they're just moving through the dust. And that movement through the dust is what's causing this illumination. So in other words, it's temporary. At some point in the future, it's going to be gone. And sometimes clusters blow away or push away with their stellar winds all of the remaining dust, and you're left with just a cluster. And this is a beautiful one called the double cluster. I think this one's a little closer to us, and this one's a little farther from us, but because the universe is in 3D. But these clusters are gorgeous, not to be confused with globular clusters. This is a globular cluster. These are called halo objects. These go around the entire galaxy. They orbit the entire galaxy. So it's really cool how that happens. And now I think you can see why it's so important for us to do this with the observatory. We want to show everybody how the universe looks in all of its various forms. And I think we're doing a good job of this, you know. Daryl is with us most nights, and Tara, you've been with us on a couple of
occasion,
nights, yeah. And when not with us on the air, she'll be in the chat. We have people from all over the world that come in and enjoy it.
It's really fun.
It is. It's beautiful. This is another composite that we did. This is called the Christmas tree cluster right here. Okay, it's a blue reflection nebula, and down here is more dark nebula. This is called, well, as you might imagine, the cone. Okay, that's the cone nebula. More dark nebula up here, and then another beautiful dark nebula, reflection nebula complex out here to the east, on the west, I mean. So this is really just a beautiful area. So, you know, and we look at, you know, we look at other galaxies like this one, the Black Eye Galaxy as well. Of course, it got a black eye.
Ouch.
Yeah, right. So we do run on public funding, of course. So if you guys are in the mood to support us, we do have a GoFundMe that's active, and it keeps us going. So anyway, make a beeline over to skytourlive.com or skytourlive.org. All right, and check us out and contact us, ask us questions. I have actually gotten a lot of contact us questions. People say, "Hey, let me ask a question," and they'll get in touch and they'll write us a question. So it's kind of cool. And hey, look, Sky Tour Radio, look at that. That's cool. So that's neat stuff. So we actually have a wonderful following. So I hope you guys will join us and enjoy everything that we're doing up there. It's very important that we do what we do. You know, we want to do this public outreach in astronomy. And for the record, and just so everybody knows, Tara down there, she is actually one of our principals in the Sky Tour live stream organization, as is Marianne Robb. And Marianne Robb, a former cop, well, she's also security. You know, not that we need it.
But we do. Oh, no.
Well, I hope not.
No.
Yeah. So that's that. And now, as far as what else we're going to talk about tonight, I think that what we want to do is talk about the James Webb Telescope images. And Daryl, you've seen these images. What did you think about these images for you?
Oh yeah, I think they're great. I think some are better than others.
Yeah.
The first batch that came out, I thought the view of the Carina Nebula was a little disappointing. I mean, it was such a small part of the greater whole. Carina Nebula is very large.
Yes, it is.
I thought the spectrographic results or spectrometer or whatever of the exoplanet atmosphere was interesting. It showed water, and the galaxy cluster was really cool. And we've already seen some results coming out now where they're showing multispectral images where they have combined like Hubble, Webb, and Shanda X-ray Observatory data together.
Yep.
That shows things that we've never seen before.
That's right.
And the best is yet to come, I'm sure. We can get into that later.
Yeah, I don't disagree. I think the best is yet to come. You know, and the purpose of the Carina Nebula one. Well, what are we talking about? We're talking about this one. This is the image released by Webb, and the beauty of this. I don't want that guy. I want. Yeah, there we are. I wanted you guys with. That's you belong here. Okay, this image is cool because what it shows us, all right, is it shows us a lot of convolutions in this area. This is an area right here above this area. This is a hollowed out area. Remember I talked about when I showed you the image of the rosette, I said the young hot stars hollow out the inside with their ultraviolet radiation and stellar winds. Well, this is what one edge of such a region looks like. This is an edge of the Carina Nebula where that happens. Now, the most important thing is this right here. That little bump represents something interesting because this radiation has been pushing down and down and down on this, and you would think that it's pushing material away. As it pushes this material away, this has resisted it. This is actually a denser region of material that could be gravitationally condensing to become a star system. And so that itself is really notable. That's something amazing that we see here. But the reason that this is a James Webb photograph. It's not a Hubble photograph. The reason that the James Webb photograph is important is because we're seeing other things in here that we've never, ever seen before.
This is true.
Right. We're seeing stars in formation that have never been seen. Some of these stars here we've never seen before. They are forming in these little cocoons of material that have been invisible to our Hubble Space Telescope's infrared sensor and to our own visual approach. So when we see these objects in here, okay, and let's just do this for now. Okay, when we see these objects, we see these here. Look at this. This beautiful object right here. Looks like a little comet. That's actually an area where a star is forming, all right? A star is forming inside many of these regions. There's one forming in here. There's one here. And there's many that are forming all throughout here that have never, ever, ever been seen before. And they form because of the fact that this material, all right, is actually being blown by the stellar winds down. And as it gets blown outward, it compresses material. It increases temperature. It causes material to go past the tipping point where it then begins to coalesce into a gravitational collection and then start the endless collapse into a star or a star system that might have planets. And that's what we're seeing here. Now, the UV radiation that's pumping out this material and literally eroding all of this material outward and away is exceedingly powerful. You would not survive there. I think, Daryl, you said yesterday? I think we talked about you said SPF 5 million or something. I think we're joking. That wouldn't even help you. It would cut right through that and just eat you in the fraction of a second if you're exposed to that, because it's like being exposed to a blast furnace. No SPF that you wear would ever protect you from that. So the point being, right now in this region, carbon-based life like us could not exist. Okay, but that doesn't mean that that it can't happen, because there's areas that have a very dark, like this dark spot right here. Okay, that dark spot you're seeing right there, that right there indicates a region where the density is high enough. And if the density is high enough, perhaps the ultraviolet radiation is being stopped. And maybe something's going on in there. All right. So something could happen. And it doesn't mean that planets can't form. It just means that life like us can't form on those planets now. But remember, the universe has time in abundance. So,
and down the road, I think, we would just scratch the surface. It seems like every other day you see Webb announce, hey, new farthest galaxy ever found.
Yeah.
And we're looking deep into the infrared to see these galaxies that we could barely see, if see at all, in the Hubble ultra deep fields. They're a piece of cake with the Webb. We're looking so far back in time and so deep into the infrared. They've all been redshifted out of visible wavelengths that you're going to hear new galaxy, farthest galaxy, every other day.
I agree with that.
And just as a mechanical sort of thing, there are parts that we haven't looked at yet that you would think would be prime time right now, like the center of the Milky Way is down in the south after sunset now. And that's where the, Sagittarius A star is, the black hole in the center of the galaxy. And it's a design constraint of the Webb that sun shield has to face directly toward the sun at all times.
To protect the sensitive infrared instruments.
Exactly. And so what the Webb can look at any one time is sort of a donut shape around it. It can't look straight over its head or look straight away from the sun. We have to wait for the Webb as we orbit the sun, and the Webb follows along with it to reveal new areas of the sky to look at inside that donut as we roll around the sun over the course of a year. So we'll be seeing new stuff coming up all the time.
Yeah. That's actually the interesting part about the Webb is like you think, well, I want to see this now. I want to see that now. Yeah, well, we all do. But we have to actually wait for the Earth to be in the right position because don't forget, as the Earth goes around the sun, the Webb too is in orbit as well, going around the sun itself, but it's 1 million miles out from us. And it's at a Lagrange point, which is like a parking spot in space, effectively. And the space it's in is not one where it can just sit there and just be happy the whole time. It's actually a spot that's actually sort of unstable. It's what's called a metastable Lagrange point. And that means that you have to use energy to keep it in that position. So it's actually executing a little like an elliptical orbit out at that Lagrange point. And it has to do that in order to stay stable as it goes around the sun. That requires fuel. So it has 20 years of fuel, and they're already looking at ways to refuel once it gets past its lifetime. The other thing, too, is that we may not have to worry about that because by then we may be mounting other expeditions with larger telescopes now that we know how to make these segmented hexagonal mirror segments that can unfold up in space and make a giant mirror out of something that's much smaller. We might do something else in the future. Keep in mind also that the Webb is suffering micrometeorite impacts. It suffered one already on one of its mirror segments, and you can clearly see the damage. When you look at the overall imagery from that mirror, you can see the damage on the images. And because the Webb has such fine resolution, it does make a difference. And it means that there's a giant piece of an image that might not be usable in some cases. Now, it's only a tiny little micrometeorite hit, but it's one of 18 mirror segments that's damaged. And it's not the whole mirror that's damaged, just a tiny little piece of that segment of the mirror assembly. So it means that, over time, we're going to end up seeing more damage occur to the Webb. And hopefully we'll get around that.
I've wondered before, I think we've talked about it a bit, that the nature of a Lagrange point, by comparison, say if you look at the orbit of Jupiter around the sun, it has the Trojan asteroids running 60 degrees ahead of and behind it, which those are Lagrange points for the planet Jupiter.
Right, but those are stable. Those are stable points as opposed to metastable points.
Yeah. But still, you wonder, well, at the L2 point for the Webb, if you're not going to have matter tend to congregate there and turn into little micrometeoroid missiles that are going to hit the telescope.
Yeah.
That's just something to think about.
That's true. So now, that was the Carina Nebula. Now, one of the things I want to mention, too, about the Carina Nebula, just to look at that again, okay? Keep in mind that everything you see here, all these tendrils and all these shapes, these are a square shape. These are created by that hot ultraviolet radiation. Okay, And this is just one nebula, all right, that we're looking at right here. It's a close-up of one nebula.
Yeah.
All right.
One tiny part of one great big nebula.
That's correct. It's actually one very small part.
Yeah.
But the reason they're showing it is to illustrate how the erosion is occurring at a smaller scale. Like this guy right here. You see this strange arc right here? That's an eroding pillar right there. This is a pillar that's eroding. We see lots of these pillars in nebulae, and that's because of erosion by hot ultraviolet radiation that's streaming down and pushing away material. The denser parts of that material can withstand it, and that's why this is still here. You see that, Tara?
Yeah, that's really interesting.
Yeah.
Well, it's just so beautiful. On top of all of that stuff it's doing, it looks so soft and
Yes.
it's just gorgeous. It's just so beautiful.
It is beautiful, if not deadly. Okay.
Oh my gosh.
I mean, if I was to title this picture, I'd call it Deadly Beauty. You know?
Hopefully someday they will shoot a mosaic of a larger portion of the nebula, if not the entire thing.
Oh, can you imagine
You know,
that?
Wow.
Hubble has done that with mosaics, and
Yep.
I'd like to see what Eta Carina looks like to the Webb,
Yeah.
and
That's probably going to happen.
homunculus and all that stuff.
That's probably going to happen too. Yeah. And all those things he's mentioning are other locations of interest to us astronomer people. So the next object that the Webb photographed and released was this. This is Stephan's Quintet. It's a group of galaxies that we have imaged in SkyTour livestream. And we talked about the Andromeda Galaxy with those two satellite galaxies and how when galaxies merge, they tend to rip each other apart. Well, if you look, you can see how these galaxies have already been in collision. They've collided with each other. They're orbiting each other. And they are part of a much greater whole, too, because we have a local group of galaxies that we're in, okay, which is a few dozen galaxies that we have in our home cluster. And then there's other clusters, and then there's super clusters of these other clusters, okay, that have been identified. And this is the one particular cluster within another much larger cluster, okay? And if you look at these shapes, you're hard-pressed to find any shape that we actually know as a regular galaxy. We believe, we understand spiral galaxies. They have the spiral arms. I don't see anything that really looks like a spiral arm system here. We know elliptical galaxies, which look like round to elongated, formless objects. This kind of looks like that, but this doesn't. This has weird gas clouds in it that are doing something strange. This does too, and this has this long arc. What are those? This has this actually looks like it's been splashed by this one going right to the center. And in fact, this galaxy has been splashed and torn apart by collisions with one of these other galaxies. So, Stephan's Quintet is actually, I'll tell you something about Stephan's Quintet that I know you don't know. Okay, you either, Daryl. Maybe you do. I gotta be careful here. You may know. Most of you know about this galaxy cluster, but you just don't know it. Okay, this set of galaxies was actually featured in a movie. Who remembers the movie? Tara, do you know the movie that they talked about?
Not off the top of my head.
Okay, and they were given the names. They were angels. They were given the names of angels in this movie. Daryl?
You got me.
All right, I got Daryl. Okay. Actually, these set of interacting galaxies actually were in the film that was a box office flop, believe it or not. And it was called It's a Wonderful Life.
Oh, okay.
Yeah. That famous movie that we all know and love was a box office flop that put the Capra Film Studio out of business.
Jimmy Stewart.
Yes, yes, exactly.
I would never have guessed that ever.
Yeah.
Now that you mention it, I do remember that vaguely. It's been a long time.
Yeah, so it's pretty cool. So yeah, but what you're seeing here is in the eyes of the James Webb Space Telescope, you're seeing what happens in the farther infrared with the structure of these galaxies being torn asunder. This is stuff we couldn't see before.
I may differ with you a bit. I don't know. It's a great image, but I think the Hubble version I like a little better than the Webb version of the Stephens Quintet.
Well, you probably look at it with different eyes than I do. I'm looking at it as furthering the science of galactic structure and understanding. And in that regard, what we're seeing here well, that's not what we're seeing. We want to see the other. What we're seeing here is something that we've never seen before in galactic interaction. So to me, this is a superstar image, but it may not be as pretty as some of the Hubble shots you saw.
Well, this may be one too that they have combined the Hubble and the Webb data.
Yeah, I don't know.
I mean, not this particular image, but I thought I saw one where they had.
They might have. At some point, we'll talk about that. But the thing is, the details we see here are interesting, and this area right here is a shock wave. It's extending outward from the collision of this galaxy with one of the other galaxies, possibly this one or possibly this one. This one, again, we don't see this in 3 dimensions. It's in 3 dimensions. Some of these are closer. Some of these are farther away. All right. And they're orbiting each other, doing things. So we're seeing a snapshot in time of a very, very slow moving behemoth of a system. Okay. So if you look at it, it's really, it's stunning in that regard when you see it that way. So this is Stephens Quintet. Obviously, these are stars that are here in our own galaxy that we're looking through to see Stephens Quintet. But I want you to look around Stephens Quintet. Look around it. What is that? What's this? What's that?
Other galaxies.
They look like galaxies.
They are.
Yeah.
Little
ones.
They're farther away, Tara.
They
might be the same size as these, but they're much further away.
Yeah.
So what does this tell us? It tells us that almost wherever you look in the sky, you can see more galaxies. And when we have the capability, we're going to be able to discover that, the early ideas were that maybe there might be 1 to 2 trillion other galaxies out there. That number might rise. But if you look around, okay, these are additional galaxies. These are all other galaxies. And these things with the diffraction spikes are the stars. Okay? So we see stars with diffraction spikes. Galaxies don't have those. So everything else we see is a galaxy in here, and we have a few stars. Now, isn't that something?
Correct me if I'm wrong, but when we look at Stephens Quintet, only 4 of the galaxies are actually interacting, are they not? One of them is a foreground object. I think the one at the bottom.
The one at the bottom, I think.
Yeah.
Yeah, these guys are in full interaction. Okay.
And I do see spiral structure, and the top one looks like a barred spiral, and the upper one in the middle also looks like a barred spiral. They are badly distorted from the gravitational interactions.
Yeah, they are. It's something though, and so this represents the best image of Stephens Quintet that shows us structures changing in galaxies in a cluster situation that we've never seen before.
Tara, I'm sorry if I interrupted you.
Oh, no, this is great. I just had a question about the stars, and you talked about the spikes coming off them. That has to do with the lens, doesn't it, off of the telescope?
Yeah,
you can count them and see how many, or what is that?
They're artifacts of the design and construction of the telescope optics.
Yeah. artifact of telescope design.
Mm-hmm.
Yeah.
Yeah.
So, so Stephen's quintet was actually quite a beautiful object, even in our telescope when we look at it with SkyTour Livestream. But we could not hope to see it like this. You have a 21-foot diameter mirror looking at a set of galaxies that are far away, and it's just a stunning study object, let me tell you. Now, going on from that, let's come back into our own galaxy, and we're going to look at what's called the Southern Ring Nebula. This is,
Wow.
yeah, isn't that beautiful?
Oh my God.
Yeah, the near-infrared camera on the James Webb Telescope was able to provide this image of this, and I want you to note this object right here, this dashed object, this lengthy object right here. I'll tell you about that in just a minute, but notice it goes right toward the center of this object. This threw off astronomers for a period of time, and I will say this: when I looked at it, I had a feeling for what it was. It turned out that it is what I thought, and I don't know how. I think that it depends how you look at things. If you look at things with alignment in mind, then this looks like it's directly aligned with these central stars that you see here, but it really isn't. What it actually is a further distant galaxy that's edge on.
Yeah.
And so when you look at this, they go, look at that. Now, depending on what light you look at this object in, you can see this outer stuff here. Or if you're careful, you can study the interior of this planetary nebula, as this is called. This is a basically when a star like the sun dies, it ejects its outer shells. And when it ejects the outer shells, those outer shells will many times build up like this, form concentric shells around the dying star. And then the central part of the star, the central star being exposed now, is very, very hot. It continues to collapse and makes the white dwarf, which ends up ionizing the gas in the nebula that makes it glow. Well, in this particular case, we have a strange object that we didn't realize existed before in this way. This is a planetary nebula, yes, but there's a second star in here. This is a closely orbiting binary pair of stars. They're going around each other. And because of the way they're going around each other, it's made this extremely strange mass ejection as it was dying. And the dying star is this one right here, the one that's to the left of center here, the reddish one. That's the star that's dying. This one here is not yet dying, but it's probably around the same mass. And when it goes, it's probably going to release another shell, and this will be an extremely complex planetary nebula at that point. But this object is really quite interesting because of the way it looks. Now, we're looking at it almost straight on, okay? But if we were to turn it to the side, it would actually look like two bowls, okay, that are connected at the bottom. So that would be more like this. It would look like two bowls connected at the bottom. That's a really odd shape, but that's what this looks like. And they do that from studying the motions of material. So they know, say, this material is, say, coming toward us, and that material, say, is going away from us. Then they can actually study the actual structure of the object when they do these studies of the gas and how it's moving. But that's the Southern Ring, and again, it has these two stars in it, as opposed to just one. Like when I showed you the Dumbbell Nebula, you noticed that the Dumbbell Nebula had that white dwarf I talked about in the center. Well, the white dwarf is like the size of the Earth, okay? And so that situation is a little different here. This star here in the red, well, this star is very hot. Okay, but it's also releasing gas, so it's in the process of going into its white dwarf stage, most likely, and hasn't gotten there yet. and we're kind of catching it sort of mid-stride, which is really, really cool. But look at the streaks. This shows you there was some really complex gas expelsions that are coming from this pair.
Could you mention what the significance of the two different images is? I assume it's from the two different infrared instruments.
I think one is at one infrared wavelength and one is at the other, and been processed to show the two stars in here.
Wow.
Yeah.
You can actually see the second star in this one. And if I can come out of this a minute, let's see if this will work. Yeah. Hey, not that. We don't want to do that. We want to show that after. But if I do this, see if this is going to work. Okay. Yeah, you can see a hint of that other star here. Okay, it's very faint, but it's there. But look at the complexity in here of all this expelled cloud here. Isn't that crazy? And
it's cool.
Truly looks 3D, doesn't it?
Yes.
And at the two different wavelengths, it's showing very different things.
Yes. And if we go over now to this guy, right, and zoom in, let me actually come back over here and go over here. Now we come back here and look at this one. Now you can see very different things. Here are the two stars that are orbiting each other, right? You say, well, look at this. Look at this thing that got expelled. What's that? There's the Edge-on Galaxy. Again, It looks like a line because it's been processed down. We've done this in SkyTour livestream too. We did it last night when looking at a globular cluster. It was processed so starkly initially that you couldn't see the separate stars near the center. But by reducing that brightness in the center, you could see the stars. But the process also, faint stuff was set aside, like the top and bottom of this galaxy should show here, but we don't see it. But
when we see that galaxy there, that's like seeing the Needle Galaxy in Coma Berenices, NGC 4565.
Yeah,
except it's much farther away.
Yeah, the Needle Galaxy is one, guys, that we actually look at with SkyTour livestream when it's available, and that's something to stick around for as well. Now, if we come over here and look at this image and look at this galaxy, you can see that you can see much more detail in it, right? Not now because I moved it away, but now you can actually see that it has a dark rift across the center. Can you see that? Maybe
and
what
a
I
bulge.
should. And yeah, that's what I'm getting at. You can see all that, and we can just go like this and make it easier to see.
And more galaxies in the background.
Yeah, there's one right here, actually. Turns out that's a galaxy. This is a galaxy.
Yep.
Okay. So that thing I talked about before, that's actually a galaxy that we were looking at. Right. So this is a beautiful image. And as always, there's so much more that meets the eye, isn't it? And this galaxy is millions upon millions of light years further beyond this nebula that we're looking at. This nebula is in our galaxy. That thing over there is a whole nother galaxy. So we're looking through existing stars, through like a veil, to see a distant galaxy and more galaxies and more galaxies. It's just absolutely incredible. So that's the Southern Ring Nebula. Now, the James Webb is also good at looking at planetary atmospheres, and it did that. It looked at this particular planet called WASP 96b. WASP is the Wide Angle Search for Planets program. And it's a very interesting program that's been ongoing for years now. And it shows off the prowess at finding the signatures of elements and compounds in a distant exoplanet system. This one is, I think, a few hundred light years away that it's looking at WASP 96b. I'd have to look up the distance, but I believe it's 100 or more light years away. But if you look, each of these dots represent a data point, and these lines up and down are what are called error bars. And so they make a curve of best fit. And the curve of best fit that you see, the blue curve, that gives astronomers an idea of what might be in there based on the general peaks and valleys. All right. So in looking at this puffy Jupiter-type planet, we noticed that this actually has the signatures of water in the atmosphere of this planet. Now, right away, that means that there's hydrogen and oxygen, although in a compound called water, right? So that means there's going to be other hydrogen compounds and probably other oxygen compounds in this atmosphere, because the star undoubtedly was able to split apart H2O molecules, just like in other planetary atmospheres, including our own. And the oxygen gets driven into other things. But this is a gas giant we're talking about. So the oxygen stays in the atmosphere or maybe makes a compound with something else. But in order to find water, this particular exoplanet search turned it up. And this is with the near-infrared system, NIRISS, okay? And this is what's called a slitless, like slitless, no slit, spectrograph. And it allows you to capture the spectrum of this distant planet. Now, just imagine that. You're looking at a star in the telescope, and all you see is the star. Now, if a planet happens to be in that region around the star, the glare of the star alone is going to hide every planet from your eyes, all the way out to beyond Pluto if you had a planet at this distance, or a star at this distance. So the fact that it can look at a specific planet that is, of course, going to be lost in the starlight some of the time is pretty impressive. So as that planet passes in front of the star, it might transit and we might see more data. But the single object slitless spectroscopy instrument on the James Webb can still pick out the planetary composition of the atmosphere. And that is just something brand new to us.
Break time.
Break time.
All right. Well, we'll be right back to continue talking about the James Webb system in just a few minutes. Stick with us.
DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
The experiencer phenomenon is happening for a lot of people just like you all over the world. People are telling very similar stories about personal encounters with non-human intelligence. The Mutual UFO Network has research, resources, and support to help you make sense of what is happening. Our experiencer community is growing every day. Join MUFON, find your friends.
Hi, I'm Austin Butler from Baz Luhrmann's new film, Elvis.
Tomorrow, all of America will be talking about Elvis Presley.
As a blood donor himself, Elvis shared the gift of life with patients in need and asked others to do the same. We're encouraging you to give blood this summer. Please visit redcrossblood.org/Elvis movie today to learn more.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact. Stay connected. Only at KGRADB.com.
Hey, welcome back to Sky Tour Radio with Tara down here and Daryl over there. Amanda will join us again next week. So we left off talking about the James Webb amazing imagery that's been produced. And the last one I want to talk about is this one right here. This is what's called the SMACS, SMACS galaxy image. And this is the image of a cluster known as SMACS 0723. Now, Hubble imaged this as well some years back, and it didn't see all the galaxies that you can see in here. All right. And I want you to look at this because there's something interesting. There's some interesting features actually of this cluster when you zoom in. And you see them right away. You notice that some of the galaxies look like they're warped. You know, some of them look like they're warped. It's almost like you're looking at them through a lens, right?
Right.
Yeah. Do you see that, Tara?
Yeah, it's like a fisheye sort of almost. Or
It isn't it? Yeah. And it's interesting because
circumpolar galaxies.
Yeah, look at that. It looks like almost like a time exposure, right? Like going around the pole or something.
Mm-hmm.
And you say, well, what would cause that? And the answer is actually stranger than fiction. It is that these galaxies that we're looking at, again, this is a James Webb image, and I'll talk more about that image in a minute, and I'm sure Daryl has some things to say. But this image, we're looking at what happens when gravity itself warps space, and it changes the direction of light heading to you from a more distant object. In other words, if we have a galaxy cluster, all right, and this galaxy cluster is right here, all right, and you have a distant object back here, all right, that's got light. As that light heads for you, this object's mass is going to gravitationally tug on space and warp space, changing the path that the light takes as it comes by you. It's going to then take a different path as it passes by that galaxy cluster. And that is due to this process called, and that gives rise to the process called gravitational lensing. So gravity is bending space, and light just follows space, follows the direction that space itself is curved. It follows the curve of space.
Yep. And in fact, some of those galaxies you're seeing so stretched like that, you're seeing multiple images of the same galaxy.
That's right. That's right. And that just depends on how close they get to the gravitational source. I'll give you a little quick test here. Okay. If we look at this object, okay, let's look at this one right up here. Okay. What do you think is the lensing source for this galaxy right here?
The thing on the right, is that what you're talking about? There?
This is the galaxy. This is the galaxy whose light is being stretched and curved, right? What do you think is the object doing the curving?
Is it that little tiny one above it?
No,
What's doing the curving?
I think it's this one right here. I think it's this one that's actually curving space and warping it around it.
It's always a trick question.
I know, isn't it? Yeah, but this, see, we're seeing, it's a grand scale warping that we're seeing here. It's happening in many places in this image. So, we see all these galaxies in this SMACS, 0723 cluster. Okay. But bottom line is this is a galactic cluster, and there's more galaxies further back behind it, and there's more galaxies in front of it. But the ones behind it, as their light passes by it, are going to get stretched and changed only because the space around this galaxy cluster is being warped. by the galactic combined gravitational pull. And that light follows the curve in the same way that a car follows the hill that it's driving on. If the car is a photon of light and the hill is the warp of space, the car is constrained to follow the hill. That is how photons work in space. That's why photons that don't have any mass and thus are not subject to gravity still get trapped by a black hole. The black hole isn't pulling in photons. No. The black hole is warping space, and the photons are following space. And when the warp gets so deep that it turns back on itself, now the light just goes around and around and around, and that's it. Once it's in there, the black hole proper below what we call the event horizon, it is not going to get out for that reason, because the warp is so deep.
Space-time.
You got it.
Okay, I have a question about that and light following gravity in space.
Sure.
Does gravity then put a speed limit on light? I mean, is it keeping it from going faster?
No. Light travels at that normal speed regardless. Okay, and that's 186,282 miles per second, or in some terms you can understand, that's 7 times around the Earth in a second. Okay, that's the speed of light, basically.
Wow.
Right, I know, right? It's fast.
Yeah.
So it's like, you get hit 7 times in the back of the head when you shine a flashlight in front of you, and it goes, if you can make it go around the Earth. But light speed is constant. That it changes slightly if it's traveling through different media. Like it is different in water, it's different in a vacuum. So when we specify the speed of light, we say in what? In a vacuum, in this case a vacuum, or in water, or through a translucent solid. I mean, the speed of light is ever so slightly different, but not enough to make any difference whatsoever, really. But if you think about how that works, all gravity's doing is warping space, and it's changing the path of these constant speed particles. So the particles are moving at a constant speed, and then they get moved. Light can't be slowed down by a gravitational field because it doesn't feel the gravitational field. It just follows the warpage of space. So light can be sidestepped from you by putting a gigantic warping object, a big gravitational field in there, like a galaxy cluster, like here. And you put a galaxy cluster like that between you and your distant object you want to see, and your object's light is going to get all stretched out and distorted like we see here, and it's not going to look very good at all, is it? Right? And that's light moving at a constant speed. It's not changing its speed at all. So the speed limit is still the speed limit, and that won't differ because of the gravitational lensing. Okay. It just changes the path that light takes to get to you.
There are some good videos on YouTube that try to explain what Tara asked, I think. Why is the speed of light the fastest you can go? Tara, is that fair to say?
Yeah, I think so. I mean, why can't it go faster? It has momentum behind it, and, or...
I'm not sure if this is the answer or part of an answer. The faster you go, this is where you get into time dilation. Basically, when you hit the speed of light, time stops.
That's
time
correct.
Does not pass.
Right, and that's a finding of general relativity,
yes.
From Einstein physics. Right. But that finding, led to a number of results. But finding out that the speed of light was exactly what it was interesting. But finding out that the speed of light could change slightly, whether going through a liquid or a solid, that was interesting too. So it showed that something was going on to impede light somewhat. It's always going to go a little slower in the other things, not faster. But it has to do with how long it takes light to get through a substance cleanly, effectively. And that's really what we're talking about here. All right. So this image right here is extremely complicated to unpack in the way the universe works. But keep in mind that these objects here that we're seeing, these are stars. Again, see the diffraction spikes? Those are just stars that we're seeing. okay, that happen to be in the field. Those are way up here in the foreground. And this galaxy is way out here. In fact, these galaxies are way out there. In fact, this whole field, let me zoom out to the field. That whole field you're seeing right there, at arm's length, is the size of a grain of sand in the sky. That's the size of this. Now, you can imagine there's an awful lot of grains of sand around the universe, around the whole sphere around you. And everywhere we look in every direction, there will be a galaxy in the image, unless we're looking at a dark nebula that blocks our view of what's beyond. Like looking toward the galactic center, for instance. We might not see a galaxy beyond, but they're there. We just don't see them.
And when we look at this in the Webb compared to the Hubble, there are many more galaxies, as you said, and we are seeing them farther back in time and farther back in space.
Yeah, and let me explain what that means too, Daryl. That's kind of an important point you're making there. When we, unless you would like to, I can do it if you'd rather. I mean, but
well, I can try a little bit.
All right, go for it.
When you look at the Hubble deep field or the ultra deep field, the dimmest little reddest dots you see are galaxies, and they have been redshifted, cosmic redshift so far back that they're about to leave the visible spectrum and become infrared only. And when we use the Webb to look farther back in space-time, it brings those no longer red but now infrared galaxies so far away and so far back in time, it brings them into visibility because it sees in the infrared.
Okay. Now, let's unpack a little bit of that too, just for people who don't understand what redshift is. Redshift is to light what Doppler shifting of sound is, to compression waves in air. Okay, in other words, what you hear with sound can be compared to what you see with light. You change the pitch of a sound when something comes towards you. You see it's coming in and it's like a higher pitch. When have you heard that before? When the train's blowing its whistle and coming at you, when it goes by you, it gets very, very low. You can imagine that if that train started to speed up and go immensely fast as it went past you, you can imagine that soon that low sound might go beyond the ability of your ears to hear it. Like, and now you can't hear it anymore because that train's going so fast past you. Okay. That's a Doppler shift, and the shifting that occurs of the sound, that pitch change, is akin to the shift in the frequency of light that we see in galaxies like this here. So when we look at these galaxies here, galaxies that are farther away from us are moving faster away from us because the universe is expanding faster, all right, the further away we look. And what that means is that these galaxies, their light is coming to us, but it's being shifted, as Daryl said, toward the red end of the spectrum, the longer wavelengths. So it's like the pitch bending of sound. They go, ew. And just like you can imagine that pitch would go into an inaudible range at some point, so too would the galaxy's light go into the invisible range to our instrumentation. So the galaxy's light would all be in the infrared, as Daryl mentioned. And that process is what we call the redshift, the speeding up of galaxies the farther away they are.
The cosmic redshift.
Yes, yeah. But the point being, it's that I think is really important here, is that the Hubble Space Telescope could see into if we're looking at, let's say, let me just do this. Let's say that we're looking at the range of the infrared to be like this, okay? The Hubble could see into this much of it, and the James Webb sees all the rest, all right? So a galaxy that's had its range shifted into the infrared could be visible to the Hubble right here, okay? But if it's shifted faster, the farther away it is, the faster the shift and the higher the redshift, and the more shifted its data is, that object in the infrared would not be visible to the Hubble. It'd be outside the range of the Hubble, but it's in the range of the James Webb out here. And that's what we do.
That's near infrared versus mid and far infrared.
That's right. And the Hubble could do a near and close to mid infrared, but we're looking at mid to far with the James Webb. And the James Webb also does near infrared as well. So we can get a very similar looking image to the Hubble images. Okay. But I promise you, if you look at the Hubble deep field of this region, which was done, you won't see all these galaxies. Some of these galaxies are not going to be here. Okay. So we're going to see, for instance, like, we'll see these galaxies here. These galaxies will all be there. But maybe this very red one, okay, it might be there, it might not be. And some of these other red ones, and some of the deepest red ones might not be here. And that's something that tells us that we're looking at data that goes further back in time.
Yep. And those are the galaxies that, as I said earlier, it seems like once or twice a week you hear that Webb has found the newest, farthest away galaxy.
Yep.
Because it's looking so much farther back in time and space that we're getting closer and closer to the formation of the first galaxies. I think they're down to a couple hundred million years now after the Big Bang itself.
Agreed. And so I think, as you point out, Daryl, this the findings, the discoveries, if it just looked at galaxies, which is actually what the Webb was designed to do, by the way, it wasn't designed specifically to look at exoplanet atmospheres. That's just something it can do. It was designed to look at the farthest galaxies back in time, and that's precisely what it's doing. But if that's all it does, it's going to revolutionize our understanding of cosmology, the way the universe evolved in the early stages, because we can actually see it happening right before our eyes. So that's something that's very interesting to me. I think that it's been a very popular topic across the astronomy channels that I've looked at and listened to. The papers written, it's just endless. But the James Webb is not just going to look at galaxies. It's going to actually look for other things. As you saw, we saw that it looked at the Stevens Quintet, all right, which is not a very distant set of galaxies. It's actually a closer set of galaxies relative to the far ones. And it was beautiful. It looked at the Carina Nebula and saw stars forming in it that we've never seen before. It looked at the Southern Ring Nebula and detected a second component that created that nebula. We would not have really figured this out unless we had the imagery and data from the James Webb. And then, of course, exoplanet atmospheres and naturally the S-Max galaxy image is just stunning.
It's interesting you don't say the SMAX galaxies, you say S-Max.
Yeah, I don't know why. I didn't call it the SMAX galaxies. That's right.
Well, S-Max sounds better, I guess.
Well, that's the catalog name, and I'm used to thinking of it in the way that I would talk about it in terms of a catalog, I guess.
Oh, well.
But that's okay. Now, I want to go to you, Tara, and ask you if you had any questions about any of this right now.
Well, how do they know which direction to look at to find the earliest galaxies?
Isn't that a good question?
They're everywhere.
That's right. That's a great question. You look far enough in any direction, and you're going to see something strange. But I'll tell you, though, that truthfully, they have to look in a place where they're not going to be, there won't be too many interfering stars and dark nebulae and so forth. So they are going to look toward areas away from the galactic plane. So you won't be looking through too much disk stuff and have views of a distant galaxy through thousands of stars. In this case, you see, we can count all the stars on one hand here. Now, naturally, as I said, the image here, no, two hands. The image here is one that is the size of a grain of sand at arm's length, an actual size in the sky. All right, but it was taken looking toward the constellation of Volans. Volans, which is in the southern hemisphere. That's why you don't know it. And it's actually an extremely tiny area of space where there's nothing in the way. Now, let me give you an idea of what you're looking at, though. I didn't really give you an idea so much about this, and I got to really do that. Okay. In this image, when you look at this galaxy cluster that's doing the primary lensing here, that galaxy cluster is 4.6 billion years old. In other words, the light that we're seeing now from that cluster left when the Earth was first forming. That's how far away it is. And that isn't all, because the galaxies that are being gravitationally lensed are further away, and many of them are red. That means that they're further into the infrared. And so many of those galaxies we're looking at, some of them are actually almost approaching just 1 billion years after the universe was formed in this particular image. And the James Webb can do even better than that.
Yeah.
So the oldest galaxies in here about 12.5 billion years old. So that's pretty cool.
Tara, if we look at the original Hubble Deep Field, the Hubble image, they just took a shot in the dark. They pointed the telescope up, I think it was somewhere in Ursa Major, if I remember right, at an apparently empty part of the sky. And they pointed the telescope, and they just let the thing sit there and run for, I forget, was it 10 days, Mark, something like that?
I don't remember the exact amount of time, but they did a long exposure.
Yeah. And they just pointed the telescope into a seemingly blank part of the sky and let it run. And then what they wound up with was the deep field, where, again, there were only 1 or 2 stars in the entire field, and everything else they saw was galaxies.
Cool.
Isn't that crazy?
Many galaxies. And that's what they've done here with the web version.
Yep. And, as you zoom in, okay, you can see even more galaxies that are in here. Every fuzzy spot is a galaxy. Every spot. The diffraction grating things, well, those are stars. Now, this is a galaxy, but it's bright enough that it's actually generating some diffraction spikes, okay, which is kind of interesting. So anyway, that's interesting. Now, I would say that I think that the most important thing for us to do is to keep tabs on what the James Webb is doing, because we have an awful lot of data that has to be waded through, and an awful lot to learn about this. So now I wanted to kind of take us to a different spot. And I'm thinking maybe now is a good time for Daryl to do the deep dive and show us a little bit about the summer sky, and where we can show some imagery that we've taken with the SkyTour Livestream telescope.
Okay.
Cool.
Indeed.
Here we go.
All righty.
Hold on.
Give me just a second here. Ta-da. Okay, this is the sky tonight from my location, Colorado Springs. And this is, about sunset, a little after 8 o'clock. And we're looking west, and here's the sun behind that tree going down. And you see that Leo has moved all the way over to the point where Leo is setting just after the sun now. And here is the planet Mercury, very low in the west after sunset. You'd probably need optical aid to pick it up, binoculars at least, not a telescope. And Leo is going away. Ursa Major is going down. Here are the Canis Venatici, the hunting dogs. Here is Boötes, the herdsman, and Arcturus. You can still see Arcturus. It's bright in the west after sunset. And here is Spica and Virgo. And Virgo is going to follow Leo down to the sunset. And we'll go to about 10 o'clock. And you see now 10 p.m. or so, Leo is gone completely and Virgo is about to set. And our attention is going to shift to the south. And here is the Milky Way and the constellation of the summer now. Virgo is going away. Boötes is not far behind. Here's Ophiuchus, and he's the serpent bearer. He's holding the snake in his arms. There is the head end of the snake. There is the tail end of the snake. When Mark talked about, he showed you the image of Ro Ophiuchi, that's right about here, just above Antares and Scorpius. And you note 10 o'clock at night now. Well, heck, 9 o'clock at night. Antares is already west of the meridian, that straight line that passes straight overhead from north to south. So Scorpius is westering already. And Scorpius, because it's the farthest south of all the zodiacal constellations, it goes away really fast now. It's pretty much gone before midnight. And it's followed by the Teapot and Sagittarius the Archer. And we'll bump it up an hour or two, and you see Sagittarius, the Teapot, is transiting the meridian by a little after 10 o'clock now. And here come the stars of fall. Interestingly, Saturn is in Eastern Capricorn now. You might remember a couple of years ago when Saturn and Jupiter were in conjunction. They were over here in far Eastern Sagittarius. And in the 2 years since, Saturn has moved on to Eastern Capricorn, almost to Aquarius. Aquarius and Capricorn actually overlap a little bit there, westernmost Aquarius and easternmost Capricorn. And hey, 10:20 at night, look, Jupiter's rising now too. Saturn will be at opposition on August 14th, if I remember correctly. That's when it's directly opposite the sun in the sky. It'll rise at sunset. It'll be on the meridian at local midnight, which means 1 o'clock in the morning if you're in daylight savings time, and it will set at sunrise. So Saturn is already pretty much at its best for the year because it's the way the orbits of the planets are around the sun, that when a planet is at opposition, the sun sets, the planet rises, and it will be on the meridian at midnight. That basically when the planet is closest to us for the year, since it's closest, it's biggest and brightest. That means it's the best time of year now to look at Saturn. And Jupiter is over in Pisces, and he'll follow a month or so later. So Saturn is at opposition on the 14th, if I remember correctly, and we'll go ahead and change the days here. And look, on the 11th of August, the moon is full. The moon is at opposition. It will be, unsurprisingly, it'll be very close to Saturn because they're both coming to opposition close to the same time, just 3 days apart. But on the 11th, the moon is full at opposition, and Saturn, you only have to wait 3 more days for it to be at opposition. And by then, the moon has moved on and will be close to Jupiter. And I'll back up again to tonight. 10:30 at night now. Well, the Milky Way is prime time. You see, here comes the Milky Way passing up through the tail of the Scorpion. There are the cat's eyes, Shaula and Lasath. Those are the stinger of the Scorpion. That's what they mean. And here is Al Nossel, the tip of the teapot, spout of the teapot. And the center of the galaxy is right there, Sagittarius A, just off the tip of the spout of the teapot. And we march on up now, following the Milky Way. Recent explorations we've done on Sky Tour Livestream. Again, we've been in Scorpius. We've been in Ophiuchus. We were at Scutum, the Shield. We looked at the Wild Duck Cluster last night. On up into Aquila, Sagitt to the Arrow, and then Vulpecula. And this is where the Dumbbell Nebula is. There is Alberio, that beautiful double star. And moving on up into Saturn, the middle of the Swan. It's the center of the Northern Cross. There is the cross right there. And you get up here to Deneb, the head of the cross, or the tail of the swan. Deneb means tail. And guess what that is? There's the North American Nebula and the Pelican Nebula right there. And when we look at, Mark showed us the Veil, and I bet he will again. The Veil Nebula sits right here. And when it's an interesting sort of thing, when this time of year, if you go out and you can see the Milky Way, if you say stand and point your right arm straight out toward the tip of the spout of the teapot, and you point your left arm straight up, you'll be pointing at Deneb. And that distance, this is 90 degrees across the sky. And when you're pointing up like this, you're pointing up at the next spiral arm over in the Milky Way galaxy. That here we're looking at the center of the galaxy. And then by the time we get up here, we're looking out into space 90 degrees away from the center of the galaxy. And we're looking clean over at the next spiral arm.
Cool.
It's very cool.
It is.
And there's one of my favorites. This is Delphinus, the dolphin.
Yeah.
You might see it's got that little kite shape to it. Delphinus, the dolphin. And I've told this before that I discovered Delphinus when I was a kid on a camping trip at the lake. I was lying on a blanket at night looking up at the sky, and I saw this little kite shape. It reminded me of a diamond bracelet at the time. And it was a beautiful dark sky, and I found out later that it was Delphinus the dolphin.
That's right. I mean, I found Delphinus when I was a kid as well. And I looked at it and I said, wow, that's so cool. And I understood it was supposed to be the dolphin. And I looked above it and I saw this other thing that had 2 stars. And then a little further down, there was one. And further down, there was another one. I was like, what's that? Well, that was Sagitta. You know,
the arrow.
The arrow right there, yeah. And then just to the upper left of Sagitta, okay, was this amazing, beautiful object, which was stunning. It was actually a gorgeous nebula that I had yet didn't even understand what it was. It was just beautiful. And, you know, again, as a kid looking with my telescope, I could see it. And I loved it. And, of course, that was what we know as the Dumbbell Nebula.
Mm-hmm.
You know, I'll show you that right here real quick. There's the dumbbell. Okay. The Dumbbell Nebula is just beautiful. And in the middle of it is that hot blue white dwarf star. That thing is the size of the Earth. And because this is several thousand light years away, to be able to see something the size of the Earth means it has to be really bright and really hot. And that's precisely what Dumbbell is. Really bright and really hot.
Mm-hmm.
Sure. Well, anyway, there you go. And
can
back
we?
to
I
you.
want to cover one more thing real quick. We go back to Solarium for a second.
I mean, yeah, sure. No, I wasn't done with you. I was just showing you this one object. So
okay.
We'll
The
come
one
back.
other thing that's happening in the next week, well, the Perseid meteor shower is going to happen.
Right.
It peaks on, I believe, the night of the 12th, morning of the 13th.
Yeah.
And 10:30 at night here, here comes Perseus rising. If you see these 3 little triangles, they're down under the crooked W of Cassiopeia. These 3 little stars right here, they represent Perseus's helmet. And the radiant point of the meteor shower is right there where the tip of my pointer is, just to the left of Perseus's magic helmet. And this gets into that whole story I've told before about Perseus and Andromeda and Cassiopeia and Cepheus. And a little farther down in the south is Cetus, the sea monster we call the whale now, that Perseus went to the rescue of his squeeze Andromeda and saved her from the sea monster. And there's Pegasus, the flying horse, that he rode to rescue her with. And when you see Perseus, the star here, he's actually holding in his hand, that's the star Algol, which means the ghoul. And Algol represents the head of Medusa, the Gorgon, you know, that he looked at her reflection in the mirror so he wouldn't turn to stone. And he whacked her head off with his magic sword and took it to turn Cetus, the sea monster, into a stone, and saved his girlfriend, and they all lived happily ever after.
What a happy story.
Hey. Well, hey, they were the Greeks. They were into stuff like that.
I know.
If you ever saw the movie Clash of the Titans, that's what it's about.
Yep.
Okay, that's it.
Cool. Well, sticking with what you were saying before, Daryl, you talked about the North America Nebula.
Mm-hmm.
And I wanted to show folks a couple of versions of that. This is from the other night. We took this the other night. This is the North American Nebula. You can see this is Florida down here. This is the Gulf of Mexico. And this is what's known as the Cygnus Wall. What? You're laughing at something, and was my picture funny? I'm laughing. Okay.
Who's laughing? I'm not laughing.
I wasn't laughing.
Oh, I thought you laughed at something, and I was waiting till you finished the joke. I didn't know what you were saying. Okay. No worries. So this is the Cygnus Wall here, and you'll notice how beautiful this is, right? And over here is the Pelican Nebula that Daryl mentioned earlier. So here's the beak of the pelican. Okay, the eye is right here. And obviously just stories and mythology and what people say they look like. It really does look like North America, doesn't it? Okay. But one of the things that I like to do is I like to look at some details in some of these objects. And when I look at some of the details, that's where the real magic seems to occur. Like here in the Cygnus Wall, okay, you see how we have this density of material, but we also have this dark dust. Again, the favorite thing of astronomers is this dark dust. That's where life itself is basically born, and we see these dark blobs right here. That's, a Bach globule right there. I had the pleasure of having Bart J. Bach as my professor for a couple of classes in astronomy. And this was one of his finds he discovered. These are condensing regions that are going to make stars at some point. So there's a lot going on in these nebulae, and that's why when we take these pictures, we just can't get enough of them. They look pretty good, though. I have to say, I think Daryl would agree that they're not bad. But I will say this.
Sorry, yes, I agree.
Oh, okay. No, that's all right.
We are the chorus, and we agree.
Yeah, right. So, but I've often wondered what these look like without the stars. So I've actually removed the stars from a great many of our photographs just to do comparisons. And this is this North American region without stars. Look at that.
Love it.
It looks like you're looking at it. It looks like you're looking at clouds in the sky. But what happens is you can see the details in this overlying nebula a little better when the stars aren't blocking the area. And so that's what I like to do. I didn't actually go through processing to correct the color and all that. But look at this. Isn't this amazing? This is such a neat look. And you can see the convolutions going on in there. And I've done that with a lot of nebulae that we've taken photos of. And it's just astonishing what's behind the stars, So that's the North American Nebula. And one of the things, let me just go to the top here and go by date modified so I can show you some things. We took this on the 1st of August. This is the Gamma Cygni Nebula. I don't have the starless version of this one, but this is how this one looks. All right. And this is another nebula that I haven't done any finished processing on, but this is the one just right out of the camera that people have on the database they can go grab, and you can too. But this again is like this beautiful dark nebula that's in front of this other bright nebula behind it, And the interesting thing is Solder, this star here, that's the star Daryl mentioned as the center of the Northern Cross. That's where this is located. And that star is bright, but it doesn't cause this nebula to glow. What's happening, it's glowing by a star that's buried probably inside this dark nebula in here. Isn't that what we found out, Daryl?
That was actually the North American Nebula, wasn't it? We talked about. It wasn't Deneb that was lighting up the nebulas. It was one hidden in the dark cloud between North America and the Pelican.
Yeah, I think that it's the same is true here. These two, the star and this nebula, are unrelated, believe it or not. They're just line of sight. Because this is about 4,500 light years away, and this one's only about 1,200 or
I think maybe 2,000 light years away, a couple thousand. So
these are just line of sight objects. So again, you got to keep in mind the universe is 3D. Definitely 3D.
Solder is Gamma Cygni, and
right.
The nebulosity is called Gamma Cygni Nebula.
Yeah, but they're unrelated, which is kind of interesting.
Right,
they're just a line of
same part of
sight thing. Yeah, a line of sight thing. Now, Daryl mentioned the Veil Nebula, and some of you in Sky Tour Livestream have certainly seen this image that we've created. This is an image of the Veil that we created. It's one piece of it. Now, it's a beautiful multicolored object. Obviously, the green represents a different chemical or element than the red. The green represents a special type of oxygen, a doubly ionized oxygen atom that creates this greenish blue color. And hydrogen makes this red color, just like we see in some of the nebulae that are stellar nurseries. And this is the Eastern Veil, as it's called. But to see the entire thing all at once, here it is. And we shot this just a couple nights ago. And we did a shot of this guy here, then a shot up here, and then a shot over here, and then a shot over here. Yep. So we had 4 exposures to make this. Had I done a 5th, we might have been able to finish it out. But as Daryl said before, and as I thought about it too, the Hubble does this too. You see, sectionals like this done with the Hubble. So, okay, we can do it too. And so we did.
That's the witch's broom on the right.
Yep.
And I love that part because it looks like a tornado. It looks like a twister.
You say that often. It does too.
And that's we compared him to Alfred Hitchcock's profile on the left. You see the face there. You see the forehead and the nose and the mouth and the chin.
Yep.
Yes, you do.
And he looks like he's smiling.
Uh-huh.
Yeah.
He looks kind of evil to me, too.
A pointy nose.
Yeah. He might be the Grinch. Who was green. All right, but here's something, too. If we zoom in on what you were talking about, Daryl, this is the Western Veil. This star, 52 Cygni, has nothing to do with the nebula. It's not associated with the nebula. It's a foreground object. Okay. This nebula, this actually, why is it here, actually? This is a supernova remnant. And if you look at this side, that's the outer expansion front of this side, and this is the outer expansion front of this. And this central stuff, again, you got to think 3-dimensionally. That could be much, much further away than both of them going in the opposite direction, or it could be closer to us. But the star that created it was somewhere in here because that star blew up about 8,000 years ago, and it started to move outward. It created this outward pressure to push this material out. As it moved out, it got very hot, and it collided with other stuff in the interstellar medium, which made it have all these convoluted shapes. And as it did that, it sparked other star formation. It sparked other shock waves, which changed the colors, made the atoms glow by ionizing them. So an awful lot happened. Now you might say, well, where is the star that did the explosion? Well, obviously, when people think of an explosion, they think it goes away. But in astronomy, when a star explodes, well, many times that star will become a neutron star or a black hole or a special type of neutron star that has a lighthouse beacon of energy on it swinging around, and we call a pulsar. But in this particular case, We don't see that. What we see, though, is somewhere around here in the middle, there is an X-ray source called Cygnus X5, not Cygnus X1, which some people think, but Cygnus X5. And it's Cygnus X5 that is the progenitor, that is the star that caused it all in there. And there should be a neutron star in there. We just can't find it and haven't found it yet. But that's the Veil Nebula.
Can we zoom in on that central portion for a second?
Sure.
No, the illuminated part to the upper right.
Up here?
Yeah, that. Okay,
That's
that
the
part
central
right
veil.
there, that's called Pickering's Triangle. And you want to see how unfair things can be. A guy named Fleming discovered Pickering's Triangle, that red and green part there near the center of the image. A guy named Fleming found it, but Pickering was the director of the observatory, so he got the credit. That sucks.
Yeah, but you know Fleming because he did get some credit somehow.
Yeah.
Yep.
Okay, that's all I have.
Yeah, and this is the western eastern veil rather, and you know you got to keep in mind we're looking at this in 3D, so this could actually be something that's moving around like this, and we're seeing it kind of like in 2D, superimposed on the sky. It could be a large shell, but seen on edge. So from one side it might look like this, from this side it looks like this possibly. So again, we don't know. It's certainly not all the same distance at all. There's no doubt about that. Right? Same thing with this. But you'll notice that the shapes are different. And the reason the shapes are different is because on their way out, the star exploded pretty much uniformly, most likely. That's the idea anyway. But on the way out into the interstellar medium, it was colliding with other stuff. And in some cases, it actually was held back. Okay, like this little weird thing right here, that means it was probably held back by something right there. Okay, that's why that made that arc as it went out. This one here, it looks like it got compressed, all right, against some outer material. There might be more denser dust in that location in the Milky Way that caused this, and so we're seeing differences in the way it looked, pretty much because of the way it blew up and moved out into the interstellar medium, hitting other stuff and then changing its shape all along the way. I want to give Tara a chance, if you had any questions about this, Tara, to chime in. Don't feel you have to sit there and just smile.
No, this is you're doing such a great job of explaining all of this stuff today. It's really cool. I do have a question about something you talked about earlier.
Okay.
It was about that like the WASP and that NIRSS.
The near infrared
yes.
spectrometer on the James Webb.
I know that they're looking for water, but on any of those searches for exoplanets, is it important or is it necessary that we find planets with salt on them? Don't we need salt, or are we looking at that?
Yeah, we do, and you know what? We can actually we can see implied in findings that salt and sodium, Na in the periodic table, is probably there. Because it's easily dislodged from, say, rock strata when water hits it. Okay, so you can get a sodium ion that just, that's a sodium ion that's missing an electron. It can go off and head off into the water. And then chlorine, I think, needs or it has an extra electron. And so sodium and chlorine combine to make sodium chloride, and that's salt. Right. Okay. So the sodium chloride, that's something that that's a solution that easily mixes with water. And so sodium chloride is, again, fundamental to our kind of life, which is carbon-based life on this planet. But is carbon-based life on other planets, does it require the same amount of salt? We can't say. We don't know.
Some of that might be because we came to be in the oceans, which are salty.
That's right.
And
Yep.
to this day, we need salt. The terrasodium, as an example, you might remember back when you messed with chemistry in junior high school that you'd take a Bunsen burner and a little spoon or a little dipper and stick it in salt and then hold it in the flame, and it turned that beautiful yellow color. That's sodium right there. Sodium is easy to see. Spectrograph, I guess.
Spectroscopically, yeah.
Yeah, and I have no doubt at all that when you look at that web image that shows the water signature, some of those other hash marks belong to other elements, and sodium is probably among them.
Yeah, that's for sure.
If you ever see a picture of down at the very large telescope, I believe, whatever it's called, European Southern Observatory, one of their telescopes shoots out yellow lasers as artificial guide stars. And those are sodium lasers, and they're incredibly bright yellow. It's a very characteristic color. Could I pose a question from chat? I know we haven't covered questions tonight, but Kathy Pernasek has a really good one directed at you, Mark. She says, on the internet, someone asked if the colors we see via the web are fake, quote unquote. Can you explain how we get those beautiful colors?
Okay, well, the colors aren't fake per se, but they're generated. Okay, we know what the colors should be, and so they start with a central color, and then they grade off the colors based on what the colors would be. At longer wavelengths, they're going to look redder to your eye. So they're trying to produce an image that looks good to your eye. So when someone says the colors are fake, that's a little harsh. They're not really fake, Kathy, but that's a wonderful question. Thank you. They are, though, generated because infrared light is light we can't even see, don't forget. So if we can't see it, how do we make it visible? Well, we have to shift it into the visible spectrum. So if you shift it a certain amount into the visible spectrum, well, then the galaxy will look like it's supposed to. Say a galaxy closer to us will look like it's supposed to look, but then you're still going to have some galaxies that look red because they are more toward the red end of the spectrum with their data. But we have to shift them into the visible spectrum in order to see them. And that, in effect, is sort of generating the colors. So that's a really good question.
Yes. You may remember back in the days of radio astronomy, I think in particular, where they first started using so-called false color images. I thought they were really funky looking and artificial and unreal. But it's the whole idea of assigned colors to things that have no color is the idea behind it. And they've gotten better at it now that we have the web, that they can choose colors that better represent what's going on. But it's the whole idea, as Mark said, that, we're giving color to things that really color is meaningless in an effort to understand them and, frankly, to make them beautiful.
Yeah, and if we didn't do that, you would end up seeing very red-looking objects and say, "What's that?" And so not the best representation of these distant objects. But again, think of it as a one-to-one shift into the visible from that far infrared. You slide it too far, and the galaxies that might look, say, whitish would look blue. And you can make those really red galaxies look normal, but now all the other galaxies that are closer to us are going to look very blue. So you have to figure out where you're going to stop that slide and figure out where you're going to put the colors.
Yeah.
Because you have to make them visible, and because they're invisible. Yep. On the infrared sensor, they're visible as data. But it's up to you to apply color to them based on how their frequency looks on the sensor, what their frequency does to the sensor.
I hate to interrupt, but the time has come to end the show.
Yes, it has.
It is 19 hours and 54 minutes, coordinated universal time. All right. Well, hey, I want to thank all of you for coming. I want to thank you too as well, Tara, for being here. And Daryl, thank you.
Sure.
While we were doing this, while you were doing your deep dive, I checked the weather out in Arizona, and it looks like we do have an overriding cirrus cloud from a storm north. So I don't think we'll be able to stream tonight, but that's the way it goes.
It's supposed to rain here.
Yeah. But Tara, thank you for your wonderful questions tonight. I want
Thank
to have you more through the whole show rather than ask questions at the end. And I think that was okay. And Daryl, thank you as always. And guys, you too, man. Thank you for coming to SkyTour Radio. Check out SkyTour live stream. If you haven't subscribed, go ahead. It's all free. Everything's free.
Yeah.
You know.
Good night, everybody.
Thanks, everyone. Take care.
We'll see you later. Good night.
Okay.